Okay, separate. That letter, or, have you started the project for 110?
I did a little bit of it,
Yeah.
and then did a little bit. Really go like energized some parts, but in some like the very beginning. Like I don't know until there's a finish.
Yeah, I tried to build this logic. It doesn't work.
You schedule for Wednesday?
I was gonna take it here.
It's up to you.
Okay, yeah.
But you would make like a,
Plug-in and.
It's when it's more than, when it's like the 1 hour test or something like that is usually.
Okay, yeah.
But I'll try to,
Yeah, it's up to you. I mean,
Okay.
you just have the option.
I'm making my.
Yeah. yeah,
Pretty much.
hopefully, we'll see how this next one goes and then maybe I'll schedule,
Okay,
but yeah.
yeah, number seven system.
Yeah, so it's kind of fine.
Instead of just going and pushing everything in one process.
That's my.
Yeah, for the third one.
Yeah.
Yeah, that makes sense. Sorry, man, I'll,
No, you get.
I'll.
I got you on 110 though. 110 and understanding. I got it.
So
One ten's my hardest class.
your first process block will handle everything without the enable. And then, but it will push the, like you would do either if statement or if then statements. And you would say like, when X does this, it gets this, right? But then you would, make a second process block
Okay.
that will then check to see if the enabler is on. So you'll have to make an enabler too.
So signal for the enabler.
Yeah, so you want to know if the enable's on or not, and then the second process block says if it's on, then it will take Y internal and give it to Y.
Okay.
And then if it's not on, it will put Y as all ones.
Okay, I see.
And then if you watch the lecture plan on Piazza,
Yeah.
Justin basically tells you exactly how to do it.
Gotcha. I know that. That's how.
He literally writes out the whole thing. It's just all kind of like, it's like he like writes it out.
I see it when you write it down, but then when I have the console in front of my face. I'm
Yeah.
like,
I can help.
that's why you pull up the slides.
I know, I have this line. It's like,
Yeah, I can help you with anything.
I got. Destroyed tonight. Second process block and.
Even before the process blocks, you have to set up your enabler. Because there's a couple of cases where like,
All right, so it is 9:30. And we're going to continue our lecture on sequential logic blocks. So last time we went over SR latches and SR latches with an enable. And now we're going to continue this discussion on sequential logic and solve that problem of our data just flowing through the latches if our timing isn't correct. So here is our D flip-flop, which is just two D latches connected to each other in this way. So now what happens is when clock is low, like here, here, let me just change the laser pointer. So when the clock is low, like here, that's when your input can change. During this whole time, your input is allowed to change. So like we see here, D turns from 0 to 1, right? And the other thing about when the clock is low, this first latch is inverted clock. So this first latch is enabled, right? When the clock is low. So when D changes, the first latch, it allows D to flow through to Q. That's what this is here. When D changes, it has some delay. and it flows through to this part here. And then it becomes stable before the clock changes. Right? So this is completely stable before the clock edge, right? And what happens when the clock changes from 0 to 1? That's disabling this first latch, right? So then it will hold the output Q no matter what happens at D while the clock is high, right? Because when the clock is high, that means that this clock is 0, and that means that it's disabled. So that means that S and R are both 0. So we hold our output, right? So then during the whole period here, this is holding the previous D, right? And that gives us some time here with the pause edge of the clock. This one is enabled now, right? So that's when it lets the DS, which is just QM, right? They're the same. They're directly connected. That's when it allows it to start passing through to QS over here. So this is how we're going to stop our data from just flowing through to the next one. Because if there's another flip-flop out here, when it flows through to this one, the next one is disabled, right? And then you have this whole entire clock period to change your inputs. You just have to make sure that the D on the inputs is stable before some time before the pause edge. Because if it's not stable before then, the latch will latch onto the previous outputs and store that instead. So you just need to make sure that it's stable before pause edge clock. And then you also need to make sure that it's stable for some time after pause edge clock in order to grab it here. So that's where the setup and hold time are going to come in, and we'll talk about that more on Friday. So this is our D flip-flop. Any questions on the D flip-flop? This timing diagram? All right, so here's our characteristic equation. So the D flip-flop is very simple. If I have D is 0 and my previous Q is 0, my next one is going to become D. Basically, it doesn't matter what the previous one is. My next value is going to become whatever the input D is. But until the next clock cycle, I'm going to store that input as Q of T for a whole clock cycle. I capture it at the pause edge, and then I capture the next input at the next pause edge. And during that whole clock cycle until the next pause edge, I output what was input the previous pause edge. So this is our storage overview. So we started with a simple SR latch, right? Basically, if we set S to 1 and R to 0, then Q would become 1. And if S was 0, R was 1, Q would become 0, right? And then if we set S and R both to 1, we run into undefined outputs until it becomes stable. But for some time while you're holding both of those to 1, it just keeps oscillating. And then we had the solution to add a clock and these AND gates as kind of enable. And that allows us to have some period when the clock is low to stabilize S and R, so we can avoid the 1-1 condition. Question.
So for the first latch and the D latch, think of SD like your D, right? When it's one, Q is one. Then when D is one, Q is one as well.
Which one are you talking about?
For the first SR latch, you could treat S like it's D latch, right? Like the variable D, because as long as S is
Yes.
one, Q is always one.
Yeah, so D is going to become S, and then R just becomes not D. Any other question? Okay, so going back to this. So this it solves our problem of 1-1 happening when we're trying to swap them as inputs around the same time. But we have to make sure our timing is correct because we should only be swapping our inputs when the clock is low. So it's still a little bit burdensome to not run into the case of 1-1. So that's why we added this inverter, so that we can make sure that S is always the opposite of R. But again, we still have to make sure that for our timing, we're only changing the input D when clock is low, so that S and R can become stable. Well, the input D and D naught can become stable before clock becomes 1. And the other thing is that we have to be very strict about our timing, because if our timing is not correct, then our inputs can propagate through multiple different latches. If the enable, which is the clock, is high for too long. So that's why we have the D flip-flop, which is just 2 D latches. One is the master, one is the servant. And this will only load the D value at the rising edge clock, because this one is enabled during the lower parts of the clock, and then this one is only enabled at the upper end when the clock is enabled as 1, and when the clock is 1, this one is disabled. So it's not letting any new input come in. It's just holding what it previously was. So this solves our problem of having to do strict timing, but it costs us twice as many gates, right? We have to have 2 D latches. But again, this is not as much of a problem today, right? We have plenty of space on chips. We can fit billions upon billions of transistors, right? All right. So the other thing is, it doesn't have to be a rising edge flip-flop. It can be a falling edge flip-flop. So what I showed you before, with the first one being inverted clock, this is the rising edge flip-flop. And the reason is this one is enabled when the clock is low. This one is enabled when the clock is high. But if you want a falling edge flip-flop, you don't put the clock invert here, you put it here, right? Because then now this one is enabled when the clock is high. This one is enabled when the clock is low. So it captures the output of this one when you go from 1 to 0 rather than 0 to 1. So you'll see both of these flip-flops depicted in this way. So it's going to be a box, right? That has input D. And then if it just has a triangle like this with no inverter here, no little bubble, this means it's a rising edge flip-flop. But if you have a bubble, that means that you're inverting the clock on the input, and underlying, it's the same thing, but you'll invert it again, right? And now This one will be enabled when the real clock is 1, and this one will be enabled when the real clock is 0. So this is how you'll see in drawings if it's a rising edge flip-flop or a falling edge flip-flop. Right. So the other thing is sometimes we may want to have the flip-flop enabled or disabled. Right? Maybe we don't always want to capture the inputs every single clock cycle. We might want to store for more than one clock cycle. So to do that, we can add an enable single. Right? So now we have clock, D, and enable. So the enable controls when new data is stored. So basically, if enable is 1, we let D to pass through the queue. But if enable is 0, then the flip-flop retains its previous state. So we can achieve this with a normal D flip-flop and this multiplexer, right? Because now, if enable is 0, I just put back into it what it previously held. But if enable is 1, then at the next rising edge clock, because this is a pause edge D flip-flop, right? I will let D go into D, which will store D rather than the previous queue. So do we see this on the enabled flip-flop? Any questions so far? Okay. So here's our comparison in terms of timings on latches and flip-flops. And here, oh, let's draw this out. So this is the output on Q for a flip-flop, and this is for a latch. And this is going to be a positive edge triggered flip-flop. So let's just look at the flip-flop first. The flip-flop is pretty simple. All you have to do is when the clock is at the pause edge, what is the input D? It's 1. So for one full clock cycle, that's what Q is. And then I reevaluate. This is the next pause edge. D is still 1. So again, for one full clock cycle, we have Q as 1. Then next pause edge, D is 0. So we change Q to be 0 for, again, a full clock cycle. And at next pause edge, it was 0 again. So for a full clock cycle, it was 0. And then pause edge here. We sample it again. And it's 1 this time. So we hold 1 for a clock cycle. Pause edge, it's 0. So we switch to 0 for one full clock cycle. Okay, so that's the D flip-flop. The latch is a little bit different, right? So for the latch, we're enabled when clock is 1, right? And we're transparent when clock is 1. So while the clock is 1, which is here, okay, Q becomes what D is. So the entire time, D happens to be 1. Right? And then when the clock becomes 0, we hold the previous value, which is 1. Okay? So while the clock is 0, we hold. Then again, the clock turns to 1, and we become transparent. and D still happens to be 1. Clock becomes 0, we pull. Clock becomes 1, we are transparent. Okay, so D was 0, so we become 0. Then clock is 0, we hold the 0. Clock is 1, D is still 0. Clock is 0, we hold. And then here's where it gets a little bit different than the flip-flop, right? So clock is 1, and while clock is 1, we are transparent, right? So D is initially 1, but while clock is still 1, D changes to 0, so we change to 0. And then while the clock is 0, we hold that 0. And then here, clock is 1 again. And there's a little bit of 0 because we're transparent. We stay 0. And then once D changes to 1, we change to 1. But D changes to 0 and clock is still 1. So we change back to 0. And then once clock becomes 0, we hold that 0. So are we all clear with the difference between the flip-flop timing diagram and the latch timing diagram? Because on one of your quizzes coming up, you'll draw something like this. I'll give you D, I'll give you clock. I want flip-flop, I want latch. Okay.
As long as for the latch, as long as the clock is 1, you'll get D, right?
Mhm.
So
When the clock is 1, the output just becomes what D is. And then when the clock changes to 0, that's when we latch onto the last outputs and keep it until clock is 1 again. So that's why it's called a D-latch. All right. So this is our question, but now instead of latches, we have flip-flops. And I'm just going to add one bit of information here. Let's assume that the propagation time from D to Q is instantaneous. So there is no propagation delay. It just happens instantaneously. Your code for today is 548. I don't see new answers anymore. Anyone still thinking about this individually? It looks like just one person, so we should switch to the peer discussion. And you can just finish thinking through it with your partner.
So you get one here. No, it's because. Okay. But it's not like that's the type of thing that I'm. It's more design, so if you might have such one, it's in most of the public, but then. Well, it's just the team goals, it's the whole about the whole guy. That's reason to about the price. You talk about probably needs to look at stuff. So it goes to the. We should have a right to just you want to take care of the guys who don't have to. That's the off. Yeah, the C's running. Because there's a job.
Well, so if it's already set to one, if we have one coming in, then we're gonna have one going zero.
This was zero.
If you want this,
You guess. Yeah, it's the next. Yeah, you just drop it. Yeah. I mentioned C. Change on the prizes versus, you know, that's I mentioned. There's the
Okay. So I think most of you guys are done discussing. And it seems like we need to talk about flip-flops more. So I'll go over this. Remember, this is the big thing, right? There's two latches inside each flip-flop. And initially, all of these are storing 0, it says, right? So that means that the second latch is holding 0, right? Then we change the input Y to 1 at the input of this flip-flop, right? So that's going to happen before the positive edge. And then the question now is, when the clocks go from 0 to 1, what is going to happen, right? So let's just talk about while it's 0, what happens. So this first flip-flop, it's positive edge triggered, so it lets the 1 in, right? While the clock is 0. But the second latch over here is disabled, right? Because clock is 0. So it's still holding the 0. So this is 0. So what comes into this latch while clock is 0? Another 0. This one, a 0 comes in here, 0 comes in here. Right? Then positive edge hits. Positive edge is when the first latch becomes disabled, second latch becomes enabled, right? So that's when we go and do this transfer. So for this one, changes to 1, but all of the others are going 0 to 0. And although this changes to 1, we are now at positive part of the clock, right? This one is disabled. It's holding the 0. So it's not letting the 1 through. So this was the big difference between flip-flops and latches. With the latch, they're just transparent when clock is 1. So depending on the propagation delay from D to Q, we were not sure how many latches it was going to go through. But we knew it was going to go through some, right? But with the flip-flops, you can't. It's stuck, right? So now we can have looser timing with our clocks, and it makes timing much more simple. Because we just need to make sure that before this positive edge, we're stable, and then a little bit after it to make sure that the first latch is completely disabled, we keep it stable for a little bit too. So that's why this one is going to be A, and the reason that it doesn't matter for both of these clocks is, like I mentioned, we're assuming D to Q is instantaneous. So it really just matters when it changes 0 to 1. So it doesn't matter how much the clock has a duty cycle, how long it is, just that it changes 0 to 1. In reality, it does matter a little bit because we're going to have this setup and hold time, but we'll talk about that later. For now, it's just important to understand that these are edge-triggered flip-flops, and whether it's pause edge or neg edge, it's going to hold that value until the next pause edge or neg edge.
So for first flip flop, if the clock starts from 0, how does it become 1 after the gate?
For the first flip-flop. Okay, so let's only think about the first flip-flop then. Okay. So while the clock is 0, we change the input Y to 1, right? And the first latch has that inverter on the clock. So it's enabled when clock is 0. So that means that it's transparent when clock is 0, right? So while the clock is 0, this becomes 1. This one is still holding 0. And while the clock is 0, because the second latch doesn't have an inverter on clock, it's disabled, right? So it's not until clock changes from 1 to 0 that we start then letting the 1 pass through into the second latch. And then it doesn't even matter what Y is changing to, right? Because once clock is 1, my first latch is holding because it's no longer enabled. And that is also why the 0 here was captured over here. Because even though that now pause edge, I changed to 1, The first latch and the second flip-flop is disabled right now. Is it a little bit better?
The inverter for the first flop, aren't they all the same?
Inside, they look like this, right?
So you would need multiple clock cycles to get that initial input through all the latches? Okay.
And I'll show you how that's helpful. So here is the first thing that we can use these flip-flops for. We can use them as registers. So if I have 4 flip-flops like this, and I change the input to say 0, 1, 1, 0, pause edge clock, it'll store 0, 1, 1, 0. So I can store multi-bit inputs, right? And then if next clock cycle, I change it to 1, 1, 0, 0, next pause edge, they would change to 1, 1, 0, 0, right? So this is how I can store multi-bits, things with multiple D flip-flops. So this is use case 1. Here is use case 2. So this is our shift register. So here, let's say that we are storing 1, 1, 0, 0, and we want to shift it to the right by 1. Or let's say, let's just do 2. This is going to your question of why that would be useful. So if we want to shift this to the right by 2, put input of 0, and let's just say that we want, well, shifting right, so we're going to pre-append zeros on the left, right? Because we're just shifting in zeros. So first clock cycle, the 0 goes into here, right? This one's going to go to here. This one's going to go to here. This 0 is going to go to here. This 0 is going to go out. That's getting shifted out. So let's reflect that. This becomes 0, 1, 1, 0. Second clock cycle, we do the same thing. This is a 1, this is a 1. This is, oh, go back. This is a 0, this is a 0. So we started out with 1, 1, 0, 0, and we ended up with 0, 0, 1, 1. So we can use this as a shift. We just wait as many clock cycles as we want to shift by. And if we wanted to pre-append 1s, we could. But in this case, we're just pre-appending 0s. And then here's another thing that we can do. We can have this bit stream like 0, 1, 1, 0, 1. And we want to recognize some pattern. So in this case, we're going to output a 1 if we see 1, 0, 0, 1, if we ever see that pattern. Because, and here, let's just change it to here, 1, 0, 0, 1. First clock cycle, right? We have a 0. So the 0 goes into here. These are all undefined first. So they're undefined, so output is undefined. Because if I can't determine what this is, it's just X. If I invert X, right, it's still X. What's X? a 0 and x and x. Well, we know it will become 0 because of the 0, but let's just continue doing this then, right? So what's next on my stream here? So the 0 comes here, the 1 comes here. So this is still going to be undefined, right? Because of undefined, undefined. Then let's get the next one in. So this was 0. And the next one is a 0. We're still undefined, right?
I thought it was the 4.
I erased the 1 because this is the 1.
Oh, that is, okay.
Yeah. Like how I'm going to erase the 0 now.
Okay.
So next cycle, I'm going to, this 0 is going to come in. It was a 0. My 1 is here. My 0 is here. And let's just erase this 0 now because it's in the register. So now I can do this evaluation. So 0 and 0 and 1 and 0. This is now 0. I've not seen my pattern, right? And that's right. But the next iteration, this becomes 1. This is 0. That 0 moves in here. This 1 moves in here. Now I have 1, 1, 1, 1 on this AND gate. So now I have seen 1, 0, 0, 1. So I can make this very simple pattern recognizer on some input stream with these flip-flops and just an AND gate, right? So if I wanted this to recognize 1, 1, 1, 1, what do I do? I want it to recognize 1, 1, 1, 1. Just remove the inverters, okay? All right. So here is another thing that we can make with our flip-flops. So this is going to now be a universal shift register rather than the I'm only shifting right with the other one. So we're going to look at, this is going to be handling 1 bit. And we're going to connect the multiple of them to handle more than 1 bit. But here we can see if clear is 1, I'm going to change what's stored in my register to 0. If clear is 0 and my input is 0, then I'm going to just keep what my previous output was. I'm not going to shift. And if clear is 0 and my S0, S1 is 1, then I'm going to shift all of my data to the left, which is a shift to the right. Then I will do that. And if it's a 1, 0, I'll shift all of the flip-flops to the right to implement shift left. And then if I have clear is 0 and S0, S1 is 1, then rather than zeroing out all my registers, I'll load in whatever's on the input to all of them. So here's what it's going to look like. On the inside. So this is just one of them, right? This is our register holding our value. And if we have clear, right? So this is clear. If it's 1, then we invert it on this AND gate. And that forces it to 0. And if clear is 0, it becomes 1 here. And then our input into the flip-flop just becomes the output of this mux. Right? Because 1 and with this, whatever this is, just becomes what that is. So that's where these selectors are coming in. So if I'm 0, 0, I just keep my output. Nothing happens. None of my shift registers change. If I am 0, 1, I'm going to get the data from the left, my left flip-flop, because I'm connected to all of these flip-flops, right? So I'm going to get this data. And if I put that data into my flip-flop now, that is a shift to the right, because I got the data from the left. And then if it's 2, I'm going to get the data from the right. And if I'm putting that in my flip-flop now, it's a shift to the left because my data came from the right. And then if I have 1, 1, which is 3, I'm loading this new input instead of using it as a shifter. I'm just loading in new data and I'm not clearing it out as all zeros. So now with this building block, and I connect them all in this way, if I want to shift right by 3, I put clear is 0, S is 1, wait 3 clock cycles. Right? If I want to shift left by 2, clear is 0, S is 2, wait 2 clock cycles. And then I can also just put an input in and then shift it. Right? So this is a universal shifter. Right. So we can also use these as counters. So this is going to go through a fixed pattern. Let's say that we start with all zeros. And then the next clock cycle, this 0, because of the inverter, becomes a 1. So I start with all zeros. 0, 0, 0. My next is 0, 0, 0. 1, 0, 0, 0. Next, it's 1, 1, 0, 0. Next, it's 1, 1, 1, 0. And then after that, it's going to be 1, 1, 1, 1, and then 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, and then 0, 0, 0, 0. And I'm just going to loop through all of these again. So I can get this fixed set of patterns to loop through very easily. And you can also implement a counter in this way, but the counter is going to be a little more complicated than just one single inverter plus the 4 bits. All right. So that is flip-flops. On Wednesday, we have the quiz, and the lab on this week is going to be SR latches and flip-flops. So you know SR latches and flip-flops now, and I'm going to go over a little bit about how to implement those things in VHDL. And it shouldn't take more than 20 minutes. Your lab this week should be faster. So I mean 20 minutes to explain the lab, not to do the lab.
High confidence.
So if you have any questions, I'll stick around for a little bit. But do make sure that you finish lab 3 before Wednesday. And do look at lab 4 before you come on Wednesday. I don't know that answer. I don't know a lot about RAM. I know RAM does not have any flip-flops. Uh-huh.
How many flip-flops are there, like approximately?